So, let's compare our two methods, right? We have two methods here for learning perceptrons. One is Rosenbrat's famous original perceptron training algorithm, and the other one, which came a little bit later, is gradient descent. Okay? So let's see. The perceptron training rule is nice. There's a theorem that says it converges to the right thing, but only if the training examples are linearly separable and my learning rate is very small. In fact, infinitesimally small for the proof to go through. Okay? Now, what happens with gradient descent, right? With the gradient descent is actually much better, right? First of all, with gradient descent, notice that we are guaranteed to converge to the minimum error whether or not the data is linearly separable. There could be any amount of noise that you want. The frontier might not even be a straight line, but we'll always do the best that we can. This is much, much better than what we had before. If you go back to this figure here, right, what happens is that if you're lucky, the minimum here is sitting on this plane, right? And the best, error is 0. On the other hand, if you're not that lucky and this thing is floating somewhere above that plane, right? You'll still get the minimum error that you can. It won't be 0, but it's much better than oscillating forever like the perceptron training algorithm does, right? So this is a big advantage of gradient descent, and one that we're going to hold on to as we go forward, right? However, we still have the same condition that the learning rate has to be small, right? You see why the learning rate has to be small again? Let's go back to this picture, right? If the learning rate is too large, let's suppose that I had a very big learning rate, then when I take this step here, right, this step here, instead of walking me only over here, it might actually overreach. In fact, on a bad day, if my step is too large, and we really at the outset don't necessarily know what it should be, I might take so let's project this all on the plane here, right? I want to take a step in this direction, right? And ideally, actually, I wouldn't take such a small step. I would take a bigger step and land right over here, right? And in fact, if I overshoot by a little bit, that's not so bad, right? Because then I'm here, and what happens is that I zigzag until I basically converge to where I need to be, okay? The big problem is if my step is way too big and then I overshoot so much that I actually wind up at a higher error point than I started, okay? So here's one way to look at this. Here's my error surface, right? Now with just one weight, and this is the error, right? I start out here, and ideally, I would like to make a jump to here, right? I'm okay with actually making a jump to here because that will zigzag to the answer. What could go wrong, right, is if the following happens. I start out here, and I make a jump in the wrong direction, but I take it so far that I go over there, right? Notice I'm actually going in the right direction, but I'm just going too far, but I've actually made my error worse. And then when I do the same thing the opposite direction, I basically spiral out of control. This is what you want to avoid, right? This is a catastrophe, right? It ends with non being output by your computer, okay? So we are willing to take a step that's too short and, take some number of steps to get there in order to avoid this. And what exactly number you should use is a deep mystery of nature, and the answer is 0.1. Well, the answer is not 0.1, but, you could use it as a starting point. It's worked for a lot of people. So, but the bottom line is we still have this issue of the learning rate, right? We have this big advantage that we are not tolerant with respect to noise, and we're tolerant with respect to the, decision surface not even being a straight line or a hyperplane, okay? But now let's look at this for a second. What exactly is the difference between these two algorithms, right? Gradient descent is much, much better, right? But let's look at the expressions, let's just lay it on the side. Let's compare the expressions for the weight updates in the two cases, right? So the weight update here is learning rate times t minus o times xi, right? Hold that in your working memory, right? As we rapidly flip back to our good old perceptron training rule, and the weight update there is the learning rate times t minus o times the value of the feature. So what is the difference between these two?
O.
O is the difference? Why is O the difference? So first of all, they look exactly the same, right? It's exactly the same expression. Somebody must be pulling the wool over your eyes, right? What is going on here, right? These algorithms are so different, but yet they look the same. So the difference is O. Why is the difference O?
I read this chapter a while ago, and that's all I remember.
Wow, you get kudos. You get 3 points for honesty.
Yeah.
Right? Hey, that's not bad, right? Having an inkling of the answer is usually the most important thing, right? The bad thing is when you have no inkling of the answer, right? So why is O the difference? You're absolutely on the right track, right? But why is O the difference?
My guess is that, if there's a single perceptron, it's either above the threshold or below, and so there's only two values. But with gradient descent, it's a combination of more than one vector.
Exactly. So you've got both the basic idea right, and also why this works from a machine learning point of view. So here's the big difference, right? Is that in the perceptron we had this step function. So my output of the perceptron, my O, was either +1 or -1, right? It's a null or none thing. You're either above the threshold or below, right? The big thing, the sneaky little thing actually that we did when we went to gradient descent is that we took out the step function. As a result of which, this is now a smooth function, right? So my O before was +1 or -1. My O now is a real number, right? So that is a big difference. And that is a very big difference for their learning. You know why? Because we have a signal. This is the key thing about the gradient descent idea, is that the gradient is your learning signal. It's the scent that you can follow to get to where you want to go, right? In the perceptron algorithm with nonlinearity, you know that you're above the threshold, but you don't know where. You could be very close, you could be very far. You don't know what the contribution of the different weights is, right? Here, you always know how much changing each weight will help or hurt, right? You have a continuous surface that leads from the badlands of wrong answers to the good place of good answers. So the fact that we took out the nonlinearity makes a huge difference, right? It makes things much easier to learn. Did everybody follow this? Small difference, big implications. At the same time, this was kind of a cheat, because what we're really trying to do here is not, so we optimized something, but we didn't optimize what we really want to optimize. What we really want to optimize is the number of errors that you make. This is a classification problem at the end of the day. It's not linear regression. We just disguised it as linear regression. So that was a little bit of a cheat there, but it's at the end of the day, it's a big improvement. Questions? Okay, so that's perceptron training rule versus gradient descent.